This equation, showing that the time between two events is longer if the two events happen at different places, in other words, if the object in question is moving, is known as the metric equation. And there are a number of experiments that show that moving objects do in fact have clocks that travel slower. For example, if we take a clock on the surface of the Earth is rotating, so that clock is going to run a little slower than a clock that was at the center of the Earth. But I could take that clock, I could take three clocks. I could leave one here at the surface of the Earth, take one on an airplane flying with the rotation of the Earth, and take a third on an airplane flying against the rotation of the Earth. This one is going to be closest to at rest compared to a point at the center of the Earth. As a result, it is going to be moving the fastest. This one will be next, and this one will be third. And atomic clocks are accurate enough that the time change you get from going clockwise around the Earth or counterclockwise around the Earth is very measurable. I wouldn't go attempting it with your own crystal watch that you use on a daily basis, but with a very accurate atomic clock, this is a very measurable difference. Also, subatomic particles, such as muons and pions, naturally decay into lighter particles. It's just one of the things they do. After a certain time frame, they change into something else. However, if they're moving at very high speeds, then the time it takes before they decay is longer than when they are at rest. In other words, their own internal clocks slow down when they are moving very fast. It's sometimes useful to take this delta x and write it as v times delta t. In that case, my equation says that c delta tau squared equals c delta t squared minus v delta t squared. I can bring the c over here and factor out the delta t on this side, and what I get is that delta tau squared is equal to the square root of 1 minus v squared over c squared times delta t. Or sometimes we would like to write sorry, I already took the square root. Sometimes we'd like to write delta t in terms of delta tau, and we say delta t is 1 over the square root of 1 minus v squared over c squared times delta tau. This text doesn't focus on it much, but this term right here is given the name gamma because it shows up so very often in relativistic transformations. Notice it's very small, or not small, it's very nearly 1 when v is much less than c. But as v approaches c, this diverges to infinity. It gets very, very large. Notice that the metric equation also puts a limit on the speed of an object. If I have a rocket ship that's able to take measurements of time between events, then this delta tau needs to be a reasonable, real time difference. But if v were bigger than c, then this right-hand side here would be negative, which means that the time squared, the proper time squared, would be negative. And the time difference itself would be imaginary. Now, we don't have any good meaning for an imaginary time difference. Rather, what this tells us is that this speed v can never be greater than the speed of light.